Newtonian and Maxwell, so this is the electrodynamics here, the electromagnetism, and the dynamics is there. The basic element in Newtonian mechanics is that all inertial frames are equivalent, are equally important, right? What do you mean? Equally important in writing down the equations of motion. If I have a frame like this, x, y, z, this is a frame I, and another frame like this is say I prime, but this guy is moving with a velocity v that is constant. That's fine, still an inertial frame, which means if you write down the equation of motion here, F equals mass times acceleration, if you write it there, F prime equals mass prime times acceleration prime, they are equivalent. The forces, if they are measured, they're going to be the same. The mass is going to be the same. The acceleration, if you put sensors, accelerometer, they're going to measure the same. They are indeed equivalent according to Newtonian mechanics. Okay? Because simply, I mean, this is a constant velocity, so when you get the acceleration, it just vanishes. But we just said that this experiment and also Maxwell equations imply that C is constant, independent of the motion of the source. Okay? This immediately contradicts this guy. It's so obvious. Because if I have here, some phenomenon or wave traveling with a velocity c in that frame, and I'm observer here, to me this guy is moving with c minus v, right? Obviously. So the velocity of this wave in that frame is c minus v, it's not c. So it depends on the motion of your frame. So it contradicts Maxwell and Michelson-Morley experiment. So the transformation that we always use in Newtonian mechanics, which we call Galilean transformation, what's the transformation? It's linear transformation. We said it's a transformation between inertial frames. So it's a constant velocity, so the position goes linearly, x prime plus vt, right? The position in that frame is indeed the position in that frame plus vt, correct? And the time, of course, is the same. I mean, we don't even mention it, right? So when you see this contradiction, you cannot maintain the constancy of the speed of light with this idea that if you're moving with constant velocity, they should be the same frame. They contradict each other, and the only resolution is that this guy has changed as well. If you transfer, if you make a transformation for the space, you have to allow the time to change. The time is not uniform. So the space changes. You must allow for the time to change so that the rate of change of the space with respect to the time is the same in both frames. Okay? So this is simply the special relativity, nothing more. So from this transformation, we will write the following transformation, which is just linear transformation, very easy. Alpha x prime plus beta t prime. And the t also transforms. So this is like gamma x prime and delta t prime. And I just want to find the four parameters, alpha, beta, gamma, and delta, and we find them from this intuition, this conceptual thing that dx by dt, and if x is fixed, x prime is fixed, then this is v, obviously. And dx by dt, the velocity in the I frame, if x prime is moving with c times t prime, if I have a phenomenon happening here with c velocity, it should occur here with the same c velocity. And you have another version of the equation if you reverse the order, so like dx prime by dt prime, and x is moving with ct, this is also c, and dx prime by dt prime is x is fixed. So this is the velocity of this guy with respect to the other, so this is negative. 4 equations in 4 unknowns, your alpha, beta, gamma, and delta, we get the transformation that x is x prime plus vt divided by 1 minus v squared over c squared. And the time transfers as well, x prime v over c squared, square root of the same thing. And this is what we call the Lorentz transformation. Okay? Any question about that? You don't need to write. Yeah, I forgot to tell that obviously starting from the Michelson-Morley, this will not be on the final or anything. Okay? This is just for culture, but it's important culture because it's very related to what we're doing of geometry and geometry of mechanics. So this is Lorentz transformation, which actually Lorentz found the very year before, just the year before, 1904. And actually, even before that, it's the exact same transformation that Voigt found like several years ago. But it's the boldness and the cosmic spirit of Einstein. So for Lorentz and Voigt, this was just a mere transformation. Lorentz was looking for a transformation that leaves Maxwell equations invariant. When you transform Maxwell equations from some frame to another, they look different, and this should not be the case. They should be the same equations, like we do with Newton's equations. So he was looking for a transformation under which the Maxwell equations doesn't change, and he found this. Voigt was doing the same for the wave equation, and he found this. For them, as mathematical physicists, this was just a transformation. For Einstein, it was much more deep. Because he said, look, now the world is really changing. Time is not relative anymore. We have time dilation. We have length contraction. Length contraction, I mean, if this guy is like 10 centimeter, if you move with a very large speed to a stationary guy, this is no longer 10 centimeter, but shorter. Length contraction, we have time dilation. If you move faster, your clock will run slower with respect to me, like the Martian movie. Okay, so he started to have all this kind of, bustle of ideas. But it's simply the Lorentz transformation. It's nothing more. Okay, so we will move on. And I have here to mention a very important thing in 1908 by Minkowski, which was actually a teacher of Einstein, teaching him mathematics, and used to call him lazy student. So right after this, Minkowski did a very important work on the geometry of the Lorentz transformation itself. So he is the first to say that, guys, space and time are no longer separate. He is the first to come up with this word, space, time, world. Space and time are lumped together. A point in the world, a world point or a world event is a combination of space and time. This is the three-dimensional space and time. Our world is 4D, and here is the geometry of it. Here is the length element. Okay? It's your dx squared, dy squared plus dz squared, and we have here c dt all squared. C is the speed of light. So here is the length element in the 4D space. Okay? So he actually recovered the special relativity from pure geometry. So it was a very interesting paper. So like, for example, the constancy of the speed of light is exactly equivalent to the invariance of the distance. Pure metric. What do you mean? I'm in a space, and I will transform by the Lorentz transformation. In that space, I'll measure some distance. If I go there, I measure the exact same distance. Which means the Lorentz transformation is an isometry, distance preserving, right? So this idea of isometry is exactly equivalent to the constancy of speed of light. So speed of light is constant if and only if this transformation is an isometry. So he recovered all the ideas of special relativity from pure geometry. But after this paper, now, if you live at that time, you should now recognize that the world is no longer 3D, right? The world is no longer 3D. It's 4D now, right? And again, if we live at that time, and studied mechanics with this maturity, we will change nothing about our conceptual understanding of dynamics. Because to us, I don't care. It's 3D or 4D or 10D, I don't care. A free particle would just move along what? Along what? Straight line. In the 4D space-time, I don't care. Right? They didn't do this, by the way. This was not done. They didn't do this in the special relativity in that time. It will come later. They were urged to do it, although it's very natural. I mean, if you wake up tomorrow morning and some people say, well, it's no longer 10D string theory, it's 12D, it's 100D, I don't care. It's just a straight line in your space, right? Okay, so now it's Einstein's general relativity. This is 1915. And he started with, again, some objectives that he wanted to achieve from the beginning of the paper, arrived at the general relativity at the end. What are these concepts that now he doesn't favor at the beginning he was not in favor to the inertial frames because they don't maintain the constants of the speed of light. So he came up with some set of transformations, the Lorentz transformations. So these frames that transform under the Lorentz transformation are privileged. We can write down the equations of motion, any phenomenon in these frames.